Great. Okay. Thank you, Leo.
Okay, thank you, Deborah. Well, this is a side project, okay, and in a very preliminary stage. So I'll talk a little bit about phase synchronization characterization with MSSA and how to extract the synchronized clusters. And then about my extremely simple, maybe naive idea, how to do it in a maybe a slightly better way. And then I will show how we could apply this to understand the behavior of a reservoir computer. Okay. So first, phase synchronization with MSSA. Think that you have, suppose that you have a system, could be in a network like this, or in a chain, given topology, and where each node is a dynamical system, okay? And from each node, you have a measurement function. You can extract a time series from the behavior of those nodes. And the question is to see if they are phase synchronized or not by only analyzing the time series that you have. Okay. So the idea of multivariate singular spectral analysis, I will be really briefly on this. You have your several time series. You can have one time series per system or several time series for each system. And you build an object known as trajectory matrix in dynamical systems analysis. Okay. So for each system, for each time series, you build this trajectory matrix in the spirit of Takens theorem using time delay embedding. Okay, you have several matrices. These matrices could be seen as vectors, each vector representing a constructed state space of each system, or could be seen as, in the right here, as lagged copies of each time series. They are almost equivalent. So you concatenate those trajectory matrices and build a full augmented trajectory matrix X. And then you perform an SVD decomposition. The idea here is that if you have X transpose time X, you can understand this matrix as a covariance matrix, okay? Or with blocks consisting of estimates of the autocovariance of each time series and cross covariance among the time series, okay, until a given lag that corresponds to your embedding dimension, okay? And the eigendecomposition of this covariance matrix is equivalent to the SVD of X. Okay. So the idea is, for example, if you have 5 oscillators, here in this case, each oscillator is a Rosler oscillator. Okay. The idea, the proposal of Grothendieck was to extract, to measure X, Y, Z of each one of those systems. For example, here for system 1, 2, 3, 4, and 5. Run this machinery, and then you have you spec the eigenvectors. When you spec the eigenvectors here, you see nothing. There is nothing here. But if you perform something called a structure or modified Werbach sortation, each segment of the eigenvectors, this is the eigenvectors from the decomposition, okay? They are split in relation to each system. This scenario here is a scenario where those 5 oscillators are not phase synchronized. They are not sharing any oscillatory modes. Okay, So the result after this modified or structured random access rotation should be something like this. The first eigenvector showing an oscillatory behavior. We call this an oscillatory mode, linked only to oscillator 4 here, for each one of each time series, okay? The second is related only to 4 as well, and they are, there is a relationship between those eigenvectors. They are in quadrature to each other, okay? So you have, for each oscillatory mode, you have 2 eigenvectors, okay? These 2 eigenvectors are related only to the second system here, and so on, okay? I will show next a scenario where you have phase synchronized clusters, okay, in a few moments. When you make this Varimax rotation, the eigenvectors, the eigenvalues, sorry, change as well, okay? And Grothendieck defined a modified participation index. I'll talk more on this in a few moments, okay? My previous presentations in the seminars in the group, I usually focused on the eigenvalues. My lesson last year was about the eigenvectors, okay? And today will be about the modified participation index, okay? I never really made any attempt to provide a contribution to the field based on the modified participation index. But today, this will be my focus. Attention. So as an example here, if you have 2 Rosler's oscillators, but in the funnel regime, that means no phase coherence, and you select different, if you change the coupling strength, when your coupling strength is weak enough, you don't have any sign of phase synchronization. Here's the X, Y, Z variable before rotation, and here is after rotation, okay? After rotation, you have one component, one segment for system 1, and another component for system 2, and so on, okay? Here we have only 2 oscillators, 2 systems, but we have several modes here because in the funnel regime, the Rosler oscillator has several frequencies associated to it, okay? If you increase the coupling strength, for example, for this value here, CV, you see that the 2 segments that were split, were linked exclusively to each system, now they are being shared by both systems, okay? So this here is a signature of phase synchronization, okay?
Leo, sorry, could you say a little bit about what's a Varimax rotation? There was a question in the chat.
Okay, yeah, it's a very old rotation applied in factor analysis since maybe 60 years ago. It's very 6 decades ago, okay? Depending on the field that you work, people call this a rotation to provide a sparse, to transform a matrix in a sparse matrix, in a sense that you have a lot of zeros on this matrix, in this matrix, okay? But when it was developed, they didn't use the concept of sparsity. They used the concept of simplicity, meaning that as a simple matrix would be a matrix with a lot of zeros, okay? To allow the factor analysts to understand better the result of a factor analysis experiment. Okay, if you change the loading matrix, simplify the structure of the loading matrix, would be much easier to interpret the results. Okay, so you take the bulk or the matrix of eigenvectors, and you make a rotation asking to maximize a function. That function, if you maximize this function, this means that you have a lot of variance along the columns and rows of the matrix, of the eigenvector matrix. Okay, so to have a high variance, you need to have a lot of zeros and something fluctuating along those zeros. Okay, and Grothendieck proposed a modification of this rotation to cope with the special structure of the concatenated trajectory matrix. Okay, I will not go further here and explain this modified Varimax rotation. Okay, maybe the bulk of my own work is regarding this special rotation. Okay, it's just a modification to accommodate the structure. Well, Grothendieck, they have a lot of other works applying this method. Okay, this is one of my favorite works about synchronization of the world economic activity. Okay, they built this map based upon the decomposition of the solitary behaviors of markets, several countries. Okay, and they apply this on climate and economic time series as well. Okay, so this approach is applied for more than 1 decade now. Okay, with this modified Varimax. Okay, before this modified Varimax, the approach is being applied more than 30 years, for more than 30 years. Okay. Well, I have some contributions to that field. They are here, and I will not pinpoint each one. Okay, but all the results that I will show here are based on slight modifications of this paradigm. Okay, that we can find in those papers. Maybe the most important here is that instead of using, for example, if you have J systems, instead of using the trajectory matrices for each variable that you measure for each system. For example, if you have the Rosler system, you can measure the X, Y, and Z variable. Instead of making a trajectory matrix for X of system 1, Y of system 1, Z of system 1, and the same way for the other systems, okay, you can make only one trajectory matrix for each system if you know that the time series that you're using is the best observable, okay, in the sense of observability theory. Okay, I will not go further on this, okay, but for the Rosler system, this is the Y variable, okay. The idea is that the best of observable in the non-linear observability approach is the observable that allows you to make the best representation of or reconstruction of the phase space of your system. Okay. So the matrices are much easier to manipulate, and the MSSA, the results of MSSA gets much better. Okay. And for us now, the result of this option is that if we have a simple structure of the rotated eigenvectors. Instead of having, for example, here, they are not synchronized. We have 4 Rosler systems, not in the Funnel regime. Here is the spiral regime. They have only one oscillatory mode each. So system 1 is represented only by Y1, and these 2 eigenvectors, they have this oscillation here. Instead of having a block for X, Y, and Z for each oscillator. So it's a little bit easier to understand. Okay, and here's the idea when you're increasing a complete strength. Okay, here the 4 oscillators are not synchronized, phase synchronized. Okay, the amplitude of the movement is not correlated. Here, this is a signature, meaning that oscillators 1 and 2 are synchronized. Okay, they're sharing this oscillatory mode here. Okay, so here you have a phase synchronized cluster, and oscillators 3 and 4 are not phase synchronized with anything. And then 3 and 4 became synchronized. You have two phase synchronized clusters. And if you increase even more the coping strength, you have all the 4 oscillators synchronized. Okay, I'm showing here on the signature that you see on the eigenvectors. You have a similar signature if you follow the eigenvalues here. Okay, I'll not go deeper on this. Everything are in the papers. And here is just a metric to allow us to understand what is happening here. This is the estimate of the observed mean frequency of each oscillator. Okay, they are becoming synchronized in frequency here. One of the advantages of using MSSA is that you don't need to estimate the phase of frequency of each oscillator. Okay, there is no single way to estimate a phase or frequency for all scenarios that you have. If you have a Lorentz system or another or complex system, dynamical system, usually you need to make estimate of phase that is specific for that system by a projection in a special plane in the phase space or something else. Okay. Hilbert transformation is not appropriate in several cases. Okay, and in the literature they use sometimes Hilbert transformation to infer the amplitude and phase of a system in a wrong way. You cannot apply in any system. Okay, and using MSSA, look, I'm not estimating any phase or frequency. Okay, you just build a concatenated trajectory matrix and search for shared modes. Okay, and the interesting thing is that these are results, a theorem that says that the eigendecomposition of that trajectory matrix will give you the best basis possible for the time series that you are making the autocovariance. Okay, it works like a Fourier transform. Okay, if you have a signal and you make a Fourier transform, you have the bases are cosines and sines. Okay, but if you make this decomposition using MSSA, the basis depends on the data, and the basis adapts to the data. Okay, so if you have, I don't remember in English the name of that time series, like teeth. Okay, if you make a Fourier transform on this, you have an infinite number of modes. But if you make a MSSA, you have just one mode with the same shape of the time series. Okay, so this is this adaptive, sorry, in that sense.
Leo, someone asked why the Hilbert transformation doesn't work.
Can we talk later about that?
Okay.
It's complicated, but I'm not saying that this not work. Okay, but you cannot have if you have a signal that you don't know exactly, you don't know nothing about that signal. If you simply apply the Hilbert transform, you could have a wrong result. Okay, I'm not saying that it will not work. Okay. Okay, so now I'll talk about synchronized clusters. So that scenario here is a benchmark often used for MSSA. Okay, here you have 10 Rosler's oscillators in the spiral regime. If they are not connected, if the coupling strength is 0, the intrinsic regime is the spiral regime. This implies in phase coherence. And you increase the coupling strength. Sorry, in this plot here, it's not coupling strength of 200. Okay, this is the index of my coupling strength. The coupling strength here is equal to 0 to 0.2, I think. Okay, so we want to know characterize the formation of phase synchronized clusters at 4 different values of this coupling strength. So assume that this first value here is 0. I have an intermediate value here. I didn't explain about the signature that we have when the clusters appears in the signature that we see in the eigenvalue here. Okay, but the general idea is that if you have one cluster, for the formation of one cluster, you have one eigenvalue to a pair of eigenvalues that will rise here. Okay, it became larger. Okay, so this is a signature that implies that possible the formation of one cluster, another cluster, and maybe another cluster here. Okay, so I selected these 4 values of the coupling strength, and below I'm plotting the eigenvectors. Okay, so here for coupling strength 0, you can see that we have only one block for each system. So this block here is for system 2, and the other eigenvector that is associated with this is that near the last one. Okay, so they are always appears in pairs. Sorry, in pairs. Here, when we have the formation of the first synchronized cluster, we see that the cluster was built upon the phase coherence, phase synchronization of oscillators 1 and 2, because they are sharing on one oscillator mode here. Increasing the coupling strength, oscillators 1, 2, and 3 are phase synchronized. Okay, and then here, at this point here, you have oscillators 1, 2, 3, 4, and 5 phase synchronized. Oscillators, I think here is 6 and 7 phase synchronized. Maybe 8, and you have 9 and 10 phase synchronized, 8 maybe in an intermittent phase synchronization with 2 other blocks, whatever. We have a signature here, okay, about the evolution of the phase clustering. Now I'm going back to the modified participation index as proposed by Groth and Gill. Okay, for this I'm using this scenario here. Okay, this scenario. So first consider the first eigenvector here. The participation index, it's like you are assessing or measuring which system is raising its hand for a given oscillatory mode. So this first eigenvector represents one oscillatory mode. And you see here that the first, second, third, until the 5th eigenvector here, they are sharing one oscillatory mode here. Okay, so the intensity of the signal here, the intensity we can define, for example, as the square of these values here are higher for oscillator 1, 2, 3, and 4, a little bit lower to oscillate to the 5th oscillator, and then almost 0 for the other oscillators. So the participation index, here's the first eigenvector. So k here is equal to 1. Okay, d means the system or the block that you're using here. So pi dk for eigenvector 1, so it's pi d1. For the first system, pi 1, 1 would be the eigenvector for this, the eigenvalue of this eigenvector, everything after rotation, okay? The star here means after rotation. This eigenvalue times this e bar squared. But this e bar squared is just the squared values here in that block D, squared and added together. Okay, so this is like how high this system is raising its hand, okay? It's high for system 1 in that sense here, okay? So for each vector k, eigenvector k, you can estimate this. And this plot here is a plot for that you can find in the seminal work of Groth and Gill for exactly the same case, okay? And here you have, here they are calling x1 because well, you can use x, y, or z. Oscillator 1, 2, 3, and 4, you see that the pi decay of them are very similar for k equals to 1 and 2. So this means that eigenvectors 1 and 2, each block for the oscillators 1, 2, 3, and 4 are similar, okay? And then you have another eigenvector here, 3, 4, with a higher participation index for oscillator 7, a little bit smaller for 6 and 8. So maybe you can consider this another cluster of phase synchronized oscillators. So you have one cluster here, 1, 2, 3, 4, in 4, a little bit less for 5, then the other cluster and another cluster, okay? So that would be the way to infer about the synchronized clusters. Okay, so imagine this in a large network. Here are the modified participation index for these 4 different conditions here, 4 different coping strengths. Okay. This is just for 10 oscillators, okay? Yeah. So now the extremely simple idea. Okay, the same scenario as before. If you consider raised-handed S and give a value of 1 for each hand, we have a row vector like this, 1, 1, 1, and 0, 0, 0, 1 until here, and 0 for the others, okay? Size 1 times J. J is the number of oscillators in your network. If we define adjacency matrix for a given eigenvector K, okay? So assuming here the first eigenvector. If we define adjacency matrix for this eigenvector here, this rotated eigenvector, as the outer product here, the matrix would be that one. Okay. This means that the oscillators, this Python counts starts from 0. So this would be oscillator 1 until 5. Okay. They are phase synchronized. The others are not phase synchronized for this first eigenvector. Okay. So that's the idea. But remember, we have more information than that. Okay. You know, 1 and 0s would be for raised hands, but you have information about how high the hand is. That information is the modified participation index. So we can assume the participation index pi dk as a vector, one vector for each k, for each eigenvector, okay, with the number d of components here, okay. If you use my approach with one variable for each system, d is equal to j, okay? If you use the original work of Groth and Gill, d and j would be different, but it's a technical detail, okay? So we will have one weighted network, adjacency matrix, for each representative of each eigenvector here, okay? We can define this. Instead of that one, that matrix, we have this adjacency matrix here. And you can play this game for all eigenvectors, okay? We will find pairwise associations of weighted adjacency matrix as expected. And you can simply add them up, okay? And remember that since we are weighting this pi here, it's weighted by the eigenvalue, and the eigenvalue is related to the strength or the amount of variance that each eigenvector explains about your data. So when you make this summation here, the last eigenvectors came with a lower loading, much lower loading. Okay, so we can transform this information here on that information here. Okay. So as the idea, again, this adjacency matrix here, matrices, they are weighted adjacency matrices. They are much easier to understand than those plots here, okay? Not much easier to understand, but now you could unleash several tools from complex network analysis to infer the structure of the networks, etc. Okay, but today I'll show only things related to visualization. So last year, July last year, I was talking about the use of other kind of rotations on MSSA. Okay, the paper was related to this was published last year as well. And the final moment, I was talking about reservoir computer. Okay, so first I need to thank Thomas Lindbergh, okay, and Thomas Juglin, because they sent to me the data about the research, and now I have the pleasure to say that the paper, their paper was published last year. My presentation last year, this was just submitted, okay, and they are the experts about reservoir computers. I'm not, okay. So I will give just a general idea. So the idea is that you have a time series of a system here. You provide this time series to your computer. The computer itself is a large dynamical system. Okay, it's a network with whose nodes are dynamical systems. Okay, and they will oscillate doing this kind of not interference. How can we say? Because of it's like a perturbation that they receive, they start to oscillate, and there is a reading matrix here that will select, give weight to the information of some of those oscillators in the network to provide an estimate of the signal of all other signal. Okay. So, for example, if you have two coupled lossless systems, here are the equations. Here is a network representation. I have two lossless systems here. You can, for example, provide Y1 of the first system to the reservoir computer and ask the reservoir computer to estimate Y2. The learning process of the reservoir computer is done only on this matrix or matrix R here. I don't remember if it's a matrix or a vector. Sorry, Thomas. The readout function, okay. Not in, here in the computer, okay. So by modifying this R until it fine tuning, the reservoir computer can provide an estimate Y2 hat for Y2. Okay. Yeah. And I'm not an expert on this. T2 and T3 are the experts, and Shannon. But they say that no one knows what happens inside this computer. It's like it's something that everyone is curious about what's happening here. And last year, so this is from July last year, using data that they gave me about, of a reservoir computer with 500 nodes. I was trying to use MSSA to search for phase synchronization inside that computer. Okay, so using the time series of each node, okay, I applied the MSSA here without rotation, here with rotation. Y1 is the time series of system 1, Y2 system 2, and R1 and 2 are 500, the time series of the network, of the reservoir computer here. Okay, here I'm plotting only the first 10 eigenvectors. Plot information regarding only the Y2, Y1, Y2, and the first 10 nodes of the reservoir computer. Okay. Because this matrix is huge. And here you can see that the reservoir, for at least the first 10 nodes, they are phase synchronized with Y1, as we expect. They are receiving directly the signal from signal Y1, and they are not phase synchronized with I2. Okay, I2 is here. But what about the other nodes? Okay, I tried to plot this matrix for the entire matrix, but it's a mess. It's too large. And July last year, I even have shown to you this plot. Okay, it's like I broke each segment of the eigenvectors, plot them together. We see structure here for all the 500 nodes of the reservoir computer. We see structure here, but it was complicated how to infer more things about that. Okay. So since in January, I had this idea and played a little bit, and I was looking for a system to apply that way to build a network from using MSSA. Okay. And Thomas 2 and Thomas 3, they gave 2 seminars about reservoir computers 2 or 3 weeks ago, and I remembered about that work, and why not just to try to now again apply this in this reservoir computer. Okay, so this is not the same data set. I have 5 or 6 different data sets that they provide me last year. Okay, so I'm using a different one. You see that that matrix here of the eigenvectors is different from that one, but the idea is the same. Okay, you have Y1 and the 10 first nodes of the reservoir phase synchronized. They have several oscillatory modes. The dynamics here is complex in that sense. And Y2 is not phase synchronized with either Y1 or the leading 10 eigenvectors. Okay, here is the corresponding participation indexes, pi decay. Okay, well, so now I can play my game. Can use the participation index to build a weighted network for each eigenvector, so the first one, second, and so on, and then add them up. I have this. Okay, and as a sanity check, you can see, okay, really, you have R2 is not phase synchronized with anyone here in that selection here, and you have Y1 is phase synchronized in different levels, okay, with all the rest. Okay, another sanity check is searching for example, here the nodes of the reservoir, the nodes R3 and R7. Okay, the phase synchronization is not so good. What's happening here? Here I'm plotting the original data, just a short segment, and we see that R3 and R7, they are sharing one oscillatory mode, a slow oscillatory mode, but they are not sharing, maybe 2 oscillatory modes they're sharing here, but there is a fast oscillatory mode from R7 that's not being shared by R3, okay? So this representation is much more powerful to provide information about what's happening in a network of oscillators, okay? Well, so now I could apply this for the whole network, all the 500 nodes. And see, I have one weighted adjacency matrix for each eigenvector. Here the participation index, it's a mess, it's impossible to infer anything from this. And here the network, okay? And we see that here's the weighted adjacency matrix in that sense of the pi decay. And we see that there is structure here. It's not just random, okay? Well, now just that warn here. So the idea is that I'm trying to just to test this tool. I did this last Friday, 2 hours of work just to test the idea, okay? So I'm very excited with the result, but the next plot should not be taken in very seriously, okay? So here is a hierarchical clustering of that same plot here, okay, which shows indeed that we have a structure there, okay? Of course, we need first to change the 4 parameters, okay? But we have a structure, very interesting structure here in the reservoir. And I have another plot, I have a life plot. The life plot that I will show now is only about this dendrogram here, okay, the clustering here. It's different because it's another tool. I'm using Plotly, and here I use it Seaborn, a package from Python, okay. Oops. Okay, so I will show this life plot. It's different. Oh no, it's not that plot. Where is the life plot? Sorry, just 1 minute. Okay, the life plot was here in my Ubuntu computer, desktop computer. Okay, I'm using my Mac computer. I don't know why the histogram is not here. Really sorry for that. Okay. Oh no, I need to load the data. Okay, sorry for that. I'm not able to show the life plot here. But in the life plot, I can zoom in, okay? And the really interesting thing is that the Y1 is somewhere here. Oops. And it is clustering with other it is phase synchronized with some of the nodes in that range here, okay? And then Y2, it's, for example, here, and it is being first, phase synchronized first with another group, a different group of nodes in the reservoir computer, okay? So it's like, there are one subset of nodes that are phase synchronized with Y1, just to remember what Y1 is. Okay. So there's two sets, one synchronized, phase synchronized with Y1, another set of nodes synchronized with Y2, and it seems that we are able to identify those sets, those different sets, and access the quality of phase synchronization that they have with Y1 and Y2. It's very interesting, and we could make several other questions about this. For example, because we think that the reservoir computer behaves like an embedding machine, maybe some nodes represent the projection of the system. This system is a 6-dimensional system, okay? One projection in a subspace related to the first floor of the system, and the other group of oscillators, a projection in this 500-dimensional embedding made by the reservoir computer, another subspace related to a projection of the second system. Okay, we can ask, for example, if you could make a good estimate of Y2 by only assessing the 2, 3, or 4 nodes that have a good phase synchronization with I2, or check if this R here that selects, that give weights to the nodes for the reconstruction of estimate of Y2, if they are capturing information from the nodes that have a higher quality of phase synchronization with Y2, and giving, for example, a zero loading, a zero weight for nodes that are more phase synchronized with a higher quality with Y1. So this opens several questions, really interesting questions. And I love this system. It's like going to another planet and you have a lot to think, things to ask about this planet. It's a beautiful system. And I need to thanks again, Thomas 2 and 3, to allow me to use this data, analyze this data. Okay. So this is it. Here, some papers. Okay, here from Thomas, Groth and Hill, all the papers. I was not using those papers here. Okay, they are important. And my final message here is that next year is the postdoc season, and I'm looking for a job. If you know about someone that could be interested on this kind of tools to analyze patterns on complex systems, okay, I will be really glad to know. So, Deborah, now with you. Thank you very much.
Thank you, Leo, very much for your talk. T2, have a question for you.
Sorry?
So thanks a lot for the talk, and thanks for analyzing reservoir computers. I was very curious about one thing. I mean, the reservoir computer is a driven system, and it has the echo state property when you're using it right, which means that the state of fully determined by the input signal. Now, the tools you're using, they are somehow coming from a context of an autonomous network of phase oscillators where synchronization happens because of the mutual interaction. But here in the reservoir computer, you do have mutual interaction, which, okay, that gives rise to the memory that it has, but still the state is largely determined. It's orchestrated by the input. Now the question is, does it make any difference, so to say, when you're applying these, you identify clusters, and knowing that all of this is mostly determined by the input? Or what does it mean?
Okay. Sorry, Thomas, but your image and voice get frozen in the middle when you start to ask your question. Could you ask me again, please? The last sentence.
Briefly speaking, it's just what does it mean, the fact that you're dealing with a driven system here, where all the responses of the individual nodes are largely determined by the drive. So you have a mix of drive and the mutual interaction between the nodes. But since your tool is coming from autonomous systems, so what do you think? What difference does it make? What interpretation do you need to apply here to the clusters that you identify?
Okay, I need to think more about that. The tools, they don't come from autonomous systems in that sense, I think. Look, you can, the idea of 10 Rosler systems, coupled Rosler systems, is the same idea of 500 nodes in the reservoir computer, okay, with the external signal coming in, okay. But I think, do you mean that, for example, your nodes, if you're not, there is no perturbation of, if there is no external signal, the nodes of your network of the reservoir, they will be in a steady state, or in a, there's not a name for it, but they will not be oscillating. Yeah. Is that sense?
Yeah, that's true.
Okay. Okay.
No, let's say,
okay, I think I got your point, because philosophically, or we can say about phase synchronization only for autonomous systems that sustain their own oscillatory behavior. If they are not able to sustain oscillatory behavior, you cannot use the concept of synchronization. Okay.
Yeah.
I understand. I think I understand now your point. Okay.
Yeah, let's say I don't doubt the applicability of the measures. I think they're really cool, and they lead to interesting new insights.
The interpretability of the thing.
But, yeah.
Maybe you cannot say that they are phase synchronized.
Yeah.
But they are I don't know which concept could we use. Maybe we can say for sure that those nodes in the reservoir computer, they're sharing the same oscillatory or several oscillatory modes with Y1. Another set are sharing several oscillatory modes with I2. Okay, this for sure we can say. But we cannot go one step or one conceptual level up saying about synchronization. But this for the questions related to understanding the behavior of the reservoir computer, it's okay. The tool is the same. But thank you to point it out.
Thanks.
Yeah, you're sure. You're right. Thank you.
Do we have other questions? Let me check on the chat. Oh, Thomas, you have your...
Yeah.
Okay.
I have my hand up for a reason, because I have a question.
Okay.
Leo, I didn't get something. Could you go back to the recurrence matrix, or this network matrix, where you exactly this one. No,
this one.
This one, yeah.
Okay.
So when you are doing this analysis, so you're taking neighboring nodes in the random network, and how do you, or can you explain to me how you actually got there from the network structure? So I can understand all of your, how you analyze the data, but you have a random network that is behaving as a reservoir computer in this case. Yeah. And so how do you actually calculate it? It looks very, very, for a random network that reservoir computer this looks very structured to me. I mean, I would say there is a lot of structure in here.
Yes, look, another question that I forgot to say that we could make in the future is a comparison in the sense of genetic differential network analysis. It's a field. We could make a differential network analysis with, contrasting the wired or physical network, that's a random network, okay, of the reservoir, with this that I called a functional network. Okay, so this would be, we could call a functional network in the sense of shared oscillatory modes. Okay, so that's not representative of the connections of the physical connection. It's a simulation. Physical connections in the reservoir. It's a representation of the shared oscillatory modes. So, in a sense, a representation of the functional network. Okay, so, I'm using the time series of each node and applying the tools that I've showed before to the Rosler oscillator.
So
okay.
I imagine if I go along one of these rows, I am at one node.
Maybe here is a like a zoom for the first 10.
Okay. Yeah. And they don't actually have to do anything with so the information on how they are actually connected does not come into play here.
No.
This is just randomly numbered, the nodes. I mean, I can see the Y's must be your inputs or something like this.
There are Y1 and Y1 and Y2. Sorry. Just a moment here. Y1 is the input of the reservoir, okay, is the Y variable of the first Rosa system. Y2, the second, the Y variable of the second order system, okay. And the nodes, the label for the nodes are R1, R2, etc.
Yeah, okay. But they are randomly, so they are not really numbered according to the connection structure and so on.
No.
Okay. No. Good. That was something that, because I find it really surprising that when you go back to the overview of all nodes again, that there seems to be something like a recurring pattern, basically. And if this would be a recurrence matrix, I would certainly say using RQA, you would find that you have a very high kind of ordered structure in the network, actually, which I find surprising in my personal opinion.
I share with you this feeling. I felt myself surprised as well, but in a sense, it's obvious. Otherwise, if you don't have this well-behaved projection or reconstruction in phase in this space, this embedding space, 500 dimensional space, the readout function would not be able to make its job, and probably the reservoir computer would not be able to work so good as it is able to work. Okay, so in a sense, I've been surprised as well, but after having the results, it's quite obvious.
I still don't think that it is that obvious in that respect, that this reservoir computer most likely was used for something like a prediction task or something like this when Thomas and Thomas were using it. In that respect, the state that you're looking at is, or the time series that you're looking at is something like a representation of what the Rössler system is doing in a high dimensional embedding, and that the Rössler system itself then should result in such a coherent synchronization structure is quite surprising. I mean, I do agree that yes, there should be synchronization in there, because otherwise all the information should be gone immediately, and maybe the fact that this is properly used for a specific task, like a forecasting task, results in such a high ordered structure.
It's also going, Thomas, if you're driving a large number of the nodes with your input signal, then you're going to get a lot of coherence from that, right? And the propagation of that input signal through the circuit to the reservoir.
But the interesting thing is that the propagation is split in two groups or several groups. Okay.
So I guess does T3 remember how many nodes he's driving here?
500.
500.
No, are you driving all 500?
No. You have because you have this V function here.
V. How many non-zero elements are there in V?
All of them are non-zero.
So you're driving everything.
Yeah.
So extreme learning kind of configuration or something like this.
But guys, look, the driving system, the driver is not the first Rössler system. Okay, here we don't have actually one Rössler system, one three-dimensional Rössler system. We have a six-dimensional system here because of the coupling. Okay, so if we forgot about numerical issues of float, 64 precision, etc., the tax theorem says that if the embedding is large enough, good enough, the embedding will capture all the dimensions, all the complexity of the attractor of the six-dimensional system, okay, using only one variable. So when we drive the reservoir using Y1, if the reservoir behaves as an embedding machine, it should have the information about the whole state space of the six-dimensional system here. in this six-dimensional system, I forgot to say one very important thing. Sorry for that. They are identical Rosler's oscillators, but the frequency, they don't share the same frequency. There's a detuning of the frequencies, okay? So when the Y1 enters the zero-hour computer, the embedding machine should split in two groups, more like two groups, okay? One representing one oscillation, and the other oscillation, okay? Because both oscillations came inside that package that we called Y1. And from Takens, when we unfold that package, making the embedding, all the information is there, all the information. So specific projections should give us the specific frequencies of each of those two Rosa systems. Okay. But I have a problem. After when I find something, I say to myself that this was obvious. I should have done this before. I'm stupid. So maybe it's not obvious, okay? But it's my way to think when I found something. Maybe it's not obvious.
Okay, great. So Leo, thank you very much for your talk, and
thank you all for coming.
Thanks everyone for coming. Just an information about next seminar. So we'll have a guest talking from Brazil next week, and for this reason, the seminar will be at 11 a.m. next week. Okay, just for you to have in mind. But I will send the information shortly. So thank you everyone, and have a nice evening, and I see you next week.
Bye-bye. Thank you all.
Thank you, Leo. Thank you, Deborah.